Alright, so the original plan was to walk you through the whole process that I went through in trying to figure out how to get beautiful orthorombic crystals of sulfur using canola oil as a solvent. Unfortunately, there's no hard data on that, and given the fact that canola oil only has to be a precise substance within a wide margin relative to something that is laboratory grade or substance that's laboratory grade, there's not going to be anything printed on the solubility of sulfur in canola oil, and I certainly couldn't find anything. So there was a long experimental process involved in trying to figure out exactly how to get those beautiful crystals.
So we are going to see how this goes. We shall see. We'll see how this goes. Once again, we shall see.
And this was the video I was going to create, but it was turning out to be heading on towards half an hour long. And that was with paring it down a significant amount. So I am shortening it a lot. And I'm going to redo most of the experiment with what I know now so that things go more smoothly and you get the whole process of the orthorombic crystal without sitting around all the way through the scientific method. Those are the lights. One moment, please. Aren't motion activated lights great? So yeah, we'll see how this goes. Alright, so in this video we are going to be creating orthorombic sulfur crystals. And ultimately I am redoing this for the benefit of the video because, well, growing orthorombic crystals takes a long time. And actually all of these little ditsy dots are orthorombic sulfur crystals. They are very, very tiny. I spent, what was it, 4 days trying to figure out how to get large orthorombic sulfur crystals. However, I don't exactly have the ideal supplies. The ideal supply would be very nice is something called carbon disulfide, which is an organic solvent that is really, really great at dissolving sulfur. What I used instead which, because it is an organic compound, does work for dissolving sulfur. Sulfur does not dissolve in water, that is. And 1 second, please. Because it does not dissolve in water, water being a polar substance, it dissolves in non-polar substances with canola oil, alcohol, diesel fuel, any of those being organic compounds. Organic compounds are pretty much by default non-polar. So I have just turned this, I can actually, let me grab these. We have 80 degrees Celsius. This was the temperature that I determined, wow, focus, to be sort of the ideal temperature for this the dissolving of the sulfur, I also discovered that the stir stick I had is able to withstand high enough temperatures to do this. And you'll notice in a second that the sulfur is going to get real cloudy. And the cloudiness was an issue I ran into over and over and over again when I was trying. You can see it has become cloudy. The top bitsy is still clear, but the top bitsy was actually at a saturated solution of oil and sulfur at room temperature. So that is the reason for the difference in color. I am sorry for swinging you all over the place. So at the moment, this is going to take a while, A, to heat up all the way, B, to then dissolve the sulfur to achieve a supersaturated solution. So in the case of the orthorombic crystals, we are going to be, instead of in both other cases, we were freezing from a melt at different temperatures. In this case, we're going from a supersaturated solution, just like what we did with our copper sulfate. Copper sulfate is an ionic compound, though, so it can dissolve in water. Sulfur is not and can only be dissolved in oil. So we're going to give this a few hours to dissolve. I'm going to do some grating, and we'll get back to this here in a sec. Alright, that took longer than it ever possibly needed to. It's now after dark, if you don't believe me. Check out across the room over there. Yeah, it's dark out that window, that little old window. Anywho, we now have, I'm just going to bring this closer. A solution, much more yellow. We still have cloudiness. All right. So, I have sent. I'm just going to keep moving you around, of course. Why not? I have since washed the watch glass, say that 5 times fast, which I am now going to heat on this hot plate along with, so I am setting this onto the hot plate. I don't need that to be stirring anymore, but I do need that to remain around 80 degrees. I'm going to wait until the bottom is beginning to feel warm already. And in the meantime, this, because it is cloudy, needs to sit for a mite bit to allow this all the particulates that are in the solution currently to settle to the bottom. If I do not do that, each of those little particulates will serve as a nucleation point for another Dinko crystal. So we end up with a ton of very, 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 very tiny crystals rather than some nice large ones. So, and to give you an idea of what a large one of these crystals looks like, I have my 2 largest crystals I have grown thus far. Let me pop this off the stand. And looking down through here, these are the 2 largest crystals I have grown that I have found. very small, seeing as this is on times 10 magnification. Probably going to give you seasickness if I keep holding this. So let this sit, let the watch glass heat. We'll be back with you in a second. All right, so I've let it sit. I decided to set this back up on the hot plate. Both items are on the hot plate. If you cannot see, I shall move you closer. So, neither is going to be at exactly 80 degrees Celsius because they're off center, and it's pretty much only the center in this case that gets really, really warm. So as you can see with our solution, squish it down, we have now, come on, a layer of what looks like almost dust on top of our pellets. So that is where we have had, the particulates have settled out, and we now have a nice clear solution, or clear-ish yellow solution, very much more yellow than, say, that. So definitely sulfur in that solution. So I am now, I'm going to set you a little bit closer than I had been. There you go. I'm going to now pour my departiculated solution into, this is now a warm watch glass. Out near the tips, it is very much barely warm. So when I overheated this in past experiments, I would get large orthorombic crystals around the edge, and I'd end up with monoclinic because the sulfur would actually melt in the middle. So right now I have this at 80 degrees. I just realized I am right in your way, so sorry. So we fill the watch glass right up on up as high as we dare. I may have dared a little bit more than I intended to dare. Set aside the beaker, nothing dangerous about that. And we can see a little better that we have very much just a clear yellow solution. So come the morning, that will be full of small crystals. And actually, as an afterthought, I'm going to let you watch me do this. I'm going to take some of the extra solution. You can see we definitely have some extra. And I've got a little pipette here. And I'm going to take just a little bit of this. Oh, got a little bit of the dust in the bottom there. And I'm going to add this to the plate that I showed you earlier, and specifically that part in the middle where I have my largest crystals. My thought is that perhaps I can get those to act as seed crystals. I don't think they're going to grow very much bigger with just that much more sulfur, but is worth the thought. We will check that out in the morning along with what happened in the watch glass. So, as always, we shall see. Alright, guys, well, per the usual, life has happened. I'm standing in a science lab in a Halloween costume dressed as a Sith Lord. I had all sorts of audio trouble trying to get this to record. I ran out of time this morning. It is now evening once again. Well, life happens. In any case, didn't hurt anything. We have crystals. So I'm going to pop you off your stand, sweep you on over here, and if this thing will focus, por favor. Well, you can kind of see we have ditsy dots. Lovely little ditsy dots. Lovely, lovely, lovely. So these are very tiny little orthorombic lovelinesses, orthorombic sulfur crystals. Now these are actually much smaller than the crystals I had last time because I actually just turned this off. I didn't try and bring this down slowly, and since oil doesn't really evaporate too well to speak of, the only way that we end up with the sulfur coming out of the supersaturated solution is through the temperature change, not through evaporation. Now, over on the microscope, the experiment with the seed crystals wasn't much of a success. You can see we have a few tiny little crystals. I'm going to try and move us up a mite bit. I have something very special to show you. If I can find it again, please let me find it again. Oh, well, that would have been one of the seed crystals. You can see it's much larger than the surrounding crystals. Oh, I'm looking for it, though. Please. Meh? Oh, is that it? Or maybe. Oh, please. Roll up. There you go. Janky microscope. Okay. In any case, we are here. This is the thing that I wanted to show you. So off to the side, we have a nice, reasonably sized orthorombic crystal, which I am blinding you with. But off to the side, we have something a tad bit more interesting. We have some monoclinic sulfur crystals. Now, the presence of monoclinic sulfur crystals isn't all that surprising. We've been working with monoclinic for a while, and it's entirely possible that the slide just got contaminated. After all, we didn't take the hot plate above 80 degrees Celsius, so we did not achieve the temperature necessary to melt the sulfur. But what is rather remarkable, you'll notice that there's something kind of weird about these monoclinic crystals. They look kind of grainy. Before they were just like sort of, I heard somebody describe them as stretched glass. But ultimately they are, or were, transparent. Here they're very grainy. They do have little patches of transparency though. Now what has happened here is, let's start with a little bit of the physics of the situation. Sulfur is only stable at the orthorombic state, at room temperature and pressure. The monoclinic form of sulfur is stable at much higher temperatures. But you would think that once you have a lovely monoclinic crystal, it will remain a monoclinic crystal no matter whether it's at room temperature and pressure or not, because, you know, it's a solid. It's not going to change form, is it? But the thing is, it does. This is called a solid state phase change. And what has happened here is the unstable monoclinic orthorombic crystals English is hard. The unstable monoclinic sulfur crystals have changed to orthorombic sulfur crystals, which are stable. Wow, the monoclinic is a solid, which I don't know about you, but I think that's pretty cool that we literally have a crystal made of crystals now. Crystalception, because life is spectacularly amazing. As you saw when I was wandering around, however, and what I was mentioning about these sulfur crystals that I grew this time around, they are more like sulfur sand. Don't get any ideas about black powder, please. So very tiny little lovelinesses, but you can still definitely tell that each and every one of these things is a tiny dinko orthorombic crystal. Like this one is particularly lovely. He's beautiful. I just called an inanimate object a he. Well done. It's been a long day, but this has been our adventure with orthorombic crystals. I will include after this some pictures of some much nicer, much larger orthorombic crystals that I got before.